Jure, or
So it was a finals week last week,
oh,
which means I need to grade today. The grades are due tomorrow, and I was away last week. That's somebody else proctored.
okay, okay.
I need to. It's the final push for everything.
How many students?
Oh, it's a graduate course. It's a
Oh,
small
okay,
course. It's
okay,
not a
okay.
big. Yeah, I don't know. 10 students.
No, not
It's
not.
easy. It will be easy. No, I should not complain. And then it's summer, so this will be good.
Okay. All right. I think you just get started, and people will pick up when they come in.
All right, sounds good. Okay, so welcome back, everybody. So it's the second day of the Lepton Flavour violation lectures. Oops, here we go. So just a reminder of the outline. So what we did yesterday was Lepton Flavour violation in the standard model, and then we talked about the observables in the muons. Then I had the lecture 3 and lecture 4 where I said I'll first do the taus and then Higgs and Flavour. I decided that I'll move Higgs and Flavour more toward the end. So we'll do taus and then searches in light new physics and then move on to Higgs and Flavour. All right, so just a short reminder of what we did yesterday. So the main messages were that in the standard model, the leptonic Flavour violation is basically 0. If you're looking at the charge decays, so if you look at mu to E gamma, mu to 3E, mu to E conversion, and as we'll see, I mean, also the ones that we'll look at today, so tau to mu gamma and so on. So if you see any signal in this charge lepton Flavour violating transitions, it will mean a discovery of new physics. And the other major thing that we saw was that there is really a big experimental push to improve on the bounds. And there's a number of experiments where orders of magnitude improvements are expected in the next decade or so. So that was the MEC2, mu to E, DME, mu to E, and COMET. So if I summarize this in one slide, so it's a different summary that we saw before. So now I'm just showing charge lepton Flavour violating modes here. And the different colorings are, the blue is when you take a dipole operator. So that's this dipole operator, which I wrote last time without the Higgs. So we had the VEV here. We see that the mu to E gamma, mu to 3E, and mu to E conversion, they all probe very high suppression scales, 10 to the 3 TeV or higher. So that's the suppression scale that sits in front of the operator. If you assume that the Wilson coefficient is 1. And then the mu to 3E and mu to E conversion were also sensitive to the this 4 fermion operators. It was either just the leptons or leptons and quarks for mu to E conversion. And again, the scale that is probed is very high. What we'll do today is we'll go over the tau Flavour changing neutral current. So the first thing you notice is that the scale that is being probed is smaller. And again, it's different decay modes will be probing different types of new physics. So if you look at tau to mu gamma, it's just the dipole. Tau to 3 mu or tau to 3E will be dipole and the 4 fermion operators. And then finally, in the lecture number 4, we'll also move to this Flavour diagonal, so Flavour conserving. So the G-2 of the electron and muon and the electric dipole moments. And you see, maybe one thing to note is that electric dipole moment is exquisitely sensitive to new physics. So it's the most sensitive if you have all the couplings or the ones, so CP violation and all the couplings or the one. All right. So what we'll do today is, it's quite ambitious. We'll see. I won't rush, so maybe I'll have to skip some of the things toward the end. I'll try to just go slow and then I'll just skip stuff if we run out of time. So we'll start with the lepton flavor violation in tau decays. Then I'll have a very short, a few slides about what you can do in BD and kaon decays if you search for lepton flavor violating mode. Then I spent quite some time on why searching for lightning physics can be interesting in these modes. And then these two topics, we'll see if I cover or not. We'll see how we go. All right, so lepton flavor violation in tau decays. So there are a few important differences compared to the muons. So the first batch is experimental. So first thing you see is that lifetime of the tau is much shorter than for the muon. So if the muon is microseconds, this is 10 to the minus 13 seconds. So it decays much more quickly. So you can't have tau beams. So experimentally, it's a big difference. Before we had muon beams, now you cannot have tau beams. So you need to have a different strategy. And the strategy is that you produce taus, they decay, and then you look at their signature. So they decay inside, relatively close to the production point. So either you produce them in the electron, E plus E minus collisions, or in the hadron collisions, PP collisions. And because of this, there will be smaller samples that you will deal with. So you will have less statistics to do the searches. The other big difference is that tau is much heavier. So it's 1.8 GeV compared to just 100 MeV. So it's 20 times heavier. Most importantly, it's heavier than many of the hadronic states. So you can have many different decay modes for tau. Then the other difference is that it's a different flavor. So there is a theoretical input that enters. So first thing that you would see is that if you have a model that produces charged lepton flavor violating decay in muons, almost always you will also have a tau decay that would accompany it. Now, often the couplings to the third generation are taken to be larger. It's because you would have this, somehow you have to get the structure of the Yukawa matrices that give the fermion masses in the standard model, and this will, in one way or the other, be reflected in new physics. So I'll give two examples later on how this works. So even though you have smaller decay branching, so you have less statistics, so you are sensitive to less rare decays in the tau case, you still may be able to probe interesting parameter space. All right, so also here there's a big jump expected in the experimental reach. So we're talking about, let's say, a factor of 50 or so almost 2 orders of magnitude. What's plotted here, there's a lot of dots. So down there, it's very hard to read. You see that there are different modes. So E gamma, mu gamma, it's always tau minus. And then at some point, oops, sorry about this. So at some point, there's hadronic decays and so on. So 3 electrons, so E plus, E minus, and an electron, and so on. So many modes. So that's illustrates the fact that I have a tau which is 1.8 GeV, and all these the magenta dots are projected sensitivities from Belle II. There is one star here which is tau to 3 muons, which is something where the high luminosity LHC measurements can have something to say about, because you can easily measure muons even in the hadronic environment. And all this is previous measurements. So Clio, Babar, where it's roughly the scale where these bounds are easy to understand just knowing what the samples of tau pairs were. So Lep had 10 to the 5, Clio had 10 to the 7, and then the B factories had more than 10 to the 8, closer to 10 to the 9, and then there will be a big jump here. No? So that's the blue bar, Belle. You see it's a slow progress in the bounds. The S tau CF is the super tau charm factor that is proposed, being discussed, let's say. All right, so we saw that there were sort of two categories of the tau decays, and the new physics that were probed, of course, will now fall into these two categories. So the first one was just purely leptonic, tau to mu gamma, tau to 3e, tau to 3 muons. So if new physics is purely leptophilic, so this couples just to leptons, that's where you would expect to see the effect. Now, there was also another set of decayed modes which involves hadrons. It would be, let's say, tau to mu and a rho meson, or tau to an electron and a rho meson, or tau to mu and a K short, so SD bar state. Now, in this case, you would need new physics that couples both to leptons and quarks. You need a Flavour violating leptonic coupling, so in the leptonic sector, while the quark couplings can be diagonal, Flavour diagonal, so that would be this, or they may also need to be Flavour of diagonal, so that would be the case where you have a K short. Another thing that is always interesting in this case is comparing with the muon decays. So if you have a concrete model with a concrete Flavour structure, there will be a relation between what you would see in muon decays and what you would see in the tau decays. All right, so I'll illustrate this on two examples. So both of them have a non-trivial Flavour structure, but it comes from in a different way. So the first one will be a model of neutrino masses where we'll look at the supersymmetric seesaw. And then I'll have another example, which is a model of Flavour. So you're trying to explain the structure of the Flavour matrices, and it will be a gauged U1 Frogat-Nielsen model. All right, so let's start with the first one. So that's the SUSY seesaw. All right, so here, what is being done is, so this model does two things for us. So it explains the smallness of the neutrino masses, and it also stabilizes the electroweak scale against quantum corrections that would push it up to the Guth scale or the Planck scale. So from practical point of view, it just means that you enlarge first the standard model with the right-handed neutrinos. So 3 generations of right-handed neutrinos. So it's the same as we had in the first lecture, where I put in 3 right-handed neutrinos to have a seesaw. But on top of this, you also double the standard model particle content with their supersymmetric partner. So an up quark will have a ups quark. So the tildes mean that they have a different statistics. So a fermion would have a scalar partner, and the bosons would have a fermionic superpartner. So it's doubled the spectrum. Now, the reason why this is interesting for us is that now there are many particles. There's a lot of couplings. There are many couplings between these particles. So there's a big chance that you'll have enhanced Flavour changing neutral currents. The chance is so big that unless you're careful, this model is killed. So if you just put in generic couplings, this model will be pushed to too high scales and has nothing to do with solving the hierarchy problem. So how many parameters? So just the minimal extension of the standard model without right-handed neutrino, so that would be the minimal supersymmetric standard model, has 124 parameters compared to the 18 or 19 in the standard model. And then there are another 18 in the neutrino sector, so neutrino and neutrino sector. Now, most of these as you see, really have to do with the fact that there's supersymmetry. You know, you need to break the supersymmetry. There are masses there, mass matrices. The form of the lepton and quark mass matrices is where most of these parameters lie. Now, what I will show is the result from Antush et al. From 2006, where they did the following. So they assumed a very restricted form of these mass matrices. So you assume that they are Flavour universal at the UV, so roughly where the cut scale is, and to the, let's say, 15, 16 GeV. And then all the lepton Flavour violation then comes from the neutrino sector, the neutrino mixing. And some of these parameters are fixed by requiring that this reproduces the neutrino masses. So you have a PMNS and the relation to the neutrino mass matrix through the seesaw relation, but not all of them. And the rest is you can scan over. Now this Flavour violation from the neutrino sector then gets fed into the lepton mass matrices using the radiative correction. So they only took the log enhanced pieces, so that's the normalization group equation. All right, so long story short, so the structure of the theory is that you have extra states. So these are the lepton, muon, and the selectron. That's the gauge boson. That would be the fermionic partner of our gauge bosons, the Z and the photon. This is the neutralino. You have a one loop correction. There's a Flavour violation denoted by this cross, which is so this diagram is written in a mass insertion approximation. So you say that there is a small off diagonal coupling between the lepton, between the muon and a selectron. So that's this cross, and this Flavour violating piece is fixed by what you assume for the Flavour structure. So there was the universality in most of it, and then all the Flavour violation was supposed to come from the neutrino sector, and then it fixes the value of this cross. No? So this then generates mu to E gamma transition. The same for tau to mu gamma transition. All right. Now there are a few things here. So the first one is that this dipole operator is actually the dominant one. So the box diagram contributions are subdominant. So this what's called the photon penguin, I like to call it the dipole. So that means that, for instance, the tau to 3 muons or mu to 3e is directly related to the radiative decay by this factor that we explained yesterday, which is just the loop factor times the phase space integration factor, right? So completely fixed. So you measure radiative decay, you will know immediately what this tau to 3 mu or tau to 3 e is. Now, the other thing was that there was this very restricted Flavour structure that you assumed. And because of this, there is a pretty strict relation between, let's say, a mu to E gamma and tau to mu gamma branching ratios. So remember, this is from 2006. So that there was less known about the neutrino mass matrix. In particular, theta 1,3 was not measured yet. So different colors here represent different assumed values for theta 1,3 in the PMNS. Theta 1,3 of 10 degrees roughly where the measured value is. So just look at this magenta blobs. On the x-axis is the branching ratio predicted for tau to mu gamma. This is the branching ratio predicted for mu to E gamma. And then in this plot, there are a few things that are fixed and a few things that are varied. For instance, the masses of the right-handed neutrinos are fixed to this 10 to the 10, 10 to the 11, and 10 to the 13 GeV. And then the mixings that are not the PMNS one, but the mixing in the right-handed sector are then varied. So that's the scan. Right? So you see that with these assumptions, there is a correlation between mu to E gamma and tau to mu gamma. Right? Now, admittedly, these assumptions are quite ad hoc. Now, there was a lot of like theory. Just you put there the structure. It's not really clear why they should be completely why you should be completely flavor blind, add the UV, and you only have the neutrino mass mixing and so on. Right. So there are other types of models where this is less ad hoc, and I'll show another example here. So that's the second example is the gauge Frogant-NISER model. Right. So the reason why here the flavor structure is not ad hoc is because this model explains the flavor structure. So the model itself will explain the flavor structure, and this will then drive all the flavor violating couplings. All right. So so this is called the standard model flavor puzzle. And it's basically two questions. So why are these fermion masses so hierarchical? What's the difference between top and up quark, electron and tau? Why are they so hierarchical? Also the neutrino masses, why are they so small? And why do we have this particular mixing pattern? Right? So one idea that is been around for a long time is due to Frogant and Nielsen. And they say that this is not a coincidence, it's a result of a symmetry that is broken. Nevertheless, it gives an imprint on the physics. So, so the structure or the explanation is the following. So we have our standard model field content, and it's all of these standard model fermions carry some quantum number. So they are charged under this additional U1 Frogant-Nielsen. So this, in this case, so I'll just call it Fn, U1 Fn. It's horizontal. Horizontal just means that different generations are charged differently. It has to do with the fact that we have this standard model field content that we draw on pictures, and usually generations are in different rows, in different columns. So you go horizontally from one to the other. Complete jargon. No? So horizontal just means you have different generations charged differently. And then on top of this, there are other fermions. They are vector-like, meaning that you have both left-handed and right-handed new fields that are charged in the same way under this new symmetry. All right. Since let's say the right-handed quarks and the left-handed quarks are charged differently, it means that there is no way you can write a standard model Yukawa now. The only way you can write down the standard model Yukawa is through a series of jumps through these heavy states. So each time you jump, there's a coupling to a scalar field phi that carries a non-zero quantum number, and that's a coupling that you can write down. All these wiggly lines are heavy modes that you integrate out. So at the end, at low energies, where you integrate out, this lambda f is the mass of these heavy fermions, phi is the VEV of the Flavor field. You will have phi over lambda f insertions to some power x. This power x is the difference of the two charges. All right, so once again, because of this global or gauge symmetry, U1 Frogant-Nielsen, you cannot write the standard model Yukawas. They are forbidden. However, there is a way to write them because there's enough of new physics states that will make the standard model fields talk to each other. And they generate this flavor structure, which is explains the hierarchy if the wave is smaller than the mass of this vector-like fermions. So if there's a hierarchy between phi and lambda f, that's an epsilon. In our case, we need this to be 0.2 to explain the standard model hierarchy. You have a model of flavor. All right, so the ingredients were, so vector-like fermions plus scalar flavor fields. So I keep here, there's no anomaly here. So now the question is whether this U1 is gauged or not. We will use this later on. And the Carr fields at the end of the chains. Now, in general, this is anomalous, but there's a version that we wrote down where you can make this non-anomalous. It's just to change the hierarchy of scales a little bit. So it's a detail. Anyway, so either global or gauged, both versions are out there. All right. Now, how do you observe this experimentally? So these extra states break flavor. They are charged under the flavor group. So the exchanges of these extra vector-like fermions or the Flavor fields or the Z prime, if it is gauge Z prime of the U1 Frogant NISER, will generate flavor changing neutral currents. So you will have a contribution to KK bar mixing from 3-level exchanges, BB bar mixing, and so on. So all of these flavons have vector-like fermions, flavorful Z prime, they all carry flavor changing couplings. Now, if you take order 1 couplings, then all these masses will be above 10 to the 7 GeV. So that tells you how strong these flavor changing neutral current constraints are, very strong. Now, if there's one exception, is that if this Z prime is light, namely the gauge coupling is small, then Z prime can be light. And then you can also search for this Z prime directly from beam dumps, E plus E minus collider, and astrophysics. All right, so let's just focus on the Z prime here and assume all the other states are heavier. There's a really a real big landscape of experiments that probe this type of models. So here I zoom in at the low energy, so below TeV, down to 10 MeV. Up here, nothing interesting happens. It's just the FCNCs are probed in the same way, all the way up to 10 to the 7 GeV, where you get to order 1 couplings. So different lines here are either you produce this in E plus E minus collisions, which are called the dark photon searches. So Z prime kind of resembles the dark photon, a photon that is so a light state that couples in the same way as the photon. Beam dumps, so you would produce them in beam dumps, have some shielding, and then look at the decays of neutral particles that penetrate the shielding. There are supernova bounds. That's from cooling of the supernova. If you cool the supernova, it will change the observed neutrino flux from 1987A supernova explosion. If you modify the mechanism of the protoneutron star. And now you see that the flavor changing bounds, which are the blue and the green lines here, and the black one, are in almost all the space. No? They are more sensitive, and they're of different varieties. So this solid green line is the mu to E conversion, where you just exchanged a Z prime here. The KK bar mixing is the flavor changing 3-level exchange between quarks. So this would be, let's say, an S and D goes to a DS state, so KK bar mixing. The dashed line is the mu to E future projection. So, on this log scale, you'll see the big improvement in reach. And then there is the blue line, which is composed of several different modes, but all of them are of the following type. So you take a meson, let's say a K, goes to a different meson, let's say a pi, and then a lepton pair, let's say mu e. So K pi mu e would be this lowest, the lowest branching ratio. Right? So, all right, so to recap, now there were many different observables here. They probe different flavor transitions, but they are all tied together because you had to, this model was there to explain the flavor structure of the standard model. That's what fixes all of these couplings up to order 1 factors. All right. Now, where are the tau decays? So let me just, so let's remember this 10 to the minus 11 here. So now the scale will change. It's good to keep the orange in your mind. So orange and green is further down. All right, so the tau decays are here. So green would be somewhere here. All right, so the tau decays right now are less sensitive. No? Also the future projections, you will never have this as the discovery modes for this particular model. However, if you discover an excess in mu to e, let's say mu to e conversion, it will be essential to also see the tau decays to understand that this is really a model that explains the standard model flavor structure, right? So to recap, so I showed you 2 examples of models where you have both tau decays and the muon decays and other flavor changing transitions. That's very typical. And I would say the models are of kind of 2 types. One is that the flavor structure is just put by hand because we defer the questions about where this standard model flavor structure came from to an even higher scale. Or if the model itself is explaining the flavor structure, then it's more rigid usually, and you really have relations that are order 1 up to factors of order 1 that you can fix. All right. So I'll spend briefly now the B to B, D, and K decays. Oh, I keep saying decays. All right. So there was this blue line there, which I said is the rare meson decays. All right. So that's an interesting set of observables, which uses not leptons as the initial state, but use hadronic state. So either K to pi mu e that I already mentioned, but then you also have B to K mu e, and so on. So there are many, many modes that you can measure here because the main gain here is that you can probe higher on-shell productions of particles. So lightning physics, because B is heavier than a kaon, and usually you gain when you have an on-shell production of the particle, which I will explain in a second. All right, so the example that I showed was a Z prime in this U1 Frogant-Nielsen. Now maybe if I don't cover, okay. So one thing to note is that if the 3-level mediator is off-shell, then the meson mixing or this lepton flavor violating efficiencies are more constrained. So that's here. Now, so that you can see from the way these lines look is that if you have a heavier guy, so at some point you are not able to produce the B to, let's say, B to K Z prime, and then Z prime decays to a lepton pair. So that's this cutoff here. No, there's no B to K Z prime production. You have to go off shell, and the scaling with the parameters changes. All right, so the coupling of Z to the final Z prime to the final state matters much more if you're off shell. In that case, you're in a regime where KK bar mixing and mu to E conversions will be the dominant probes, right? Now, if you are able to produce a Z prime, then the decays, so for onshore Z prime production, then this M1 to M2 Z prime gives the leading constraints typically, right? So the scaling changes and you're in two different regimes, right? Now, the other thing to note is that it doesn't have to be a flavor violating decay on the leptonic side. No? So also the decays of the form B2K mu plus mu minus, or even B2K neutrinos, mu bar, they can be very interesting. It all depends on what exactly the model is. No? Also, you don't have to think of Z prime. There are other, scalars and so on. Right? The important thing is that light versus heavy really pushes you to different regimes. Okay. Another example for in this case that I want to point out is it's not strictly flavor violating, but yes.
So yeah, so maybe I probably should know the answer to this, but if you go back to the previous slide, when we have these light Z primes, right? How are we evading other bounds? Like, because are we just saying it's purely flavor violating, lepton flavor, or
no. Okay, yeah.
So what about its flavor symmetric couplings?
Yeah. Okay, this was maybe not clear enough. So these colored regions, they are probing different, mostly, but really only. No? It's a very small contribution from the flavor relation. This is flavor diagonal pieces, okay? So the orange one, maybe I go back so I have more diagrams. All right, so, so this orange one, what it does is just, let's say this would be an LHC search for mu plus mu minus bump in their mu plus mu minus spectrum. Right, so that will be one of these orange shaded regions. The other one is Babar, and so on. No? And you can do either mu plus or E plus E minus search, BAM hunt. So this is flavor diagonal, and the couplings are roughly of the same size in this case. They're all the one factors that come from flavor structure here, okay? But apart from that, it's really just the play between how sensitive your flavor changing neutral current experiments are. They're much more sensitive. So that's why this green and the black lines are below these other constraints. The interesting thing is that beam dumps are almost as sensitive as the flavor changing neutral current constraints. And which one is more sensitive will depend on the details. So beam dumps are sensitive because you have a lot of protons or electrons that are being dumped on the target. So it's just the fact that you dump the beam. There's a lot of statistics that you gain. You put shielding in front and a detector afterwards. If the couplings are small enough, so that's why there's an upper bound here. No, if the couplings are small enough, the Z prime will penetrate the shielding and deposit some energy, like it will decay, let's say, into E plus E minus inside your detector now. So that's the lower limits are couplings are too small. You have nothing that is either being produced or in decays, or this upper bound here is because the couplings are too big and you cannot penetrate the wall. Then there's the supernova bounds that are, if you cool the proton neutron star, so at the beginning of the supernova explosion, the neutrinos that you see at later times, they come from the inner part of this supernova, and you would if you cool the core, you will not have this neutrino flux because they're thermal. Now there are also two lines here. So the upper one is the coupling is too big and Z prime can't escape the proton neutron star, so you don't cool it. If it escapes, you cool it, but if the coupling is too small, you don't cool it enough. So there's this kind of sweet spot where you can put the bounds. And it depends also, it's only one measurement, no? There's one supernova that exploded when we had detectors, particle detectors. You can argue that this was not the usual, the usual explosion, where it was rather a thermonuclear explosion where you don't have this effect. So these are more suspect, while the rest are lab experiments. So there's nothing to argue about. I would say the surprise is actually that the flavor diagonal are very sensitive. That was the surprise for me, at least. Usually, you just assume that the flavor changing neutral parents just, they dominate, but it's not the case here.
Okay. No, I understood.
Yeah, and the other thing that I talked about is this line shape, and you can understand this from the fact that you can't produce these guys on shell. So then your sensitivity really drops if you can't produce them on shell. I don't know if this makes sense.
Yeah, maybe now this.
Maybe I should explain.
Now the shape of this rare meson decay line, these steps are to do with when you can get a new type of meson, right? This would be like the lightest is pions and things or something, right?
So this is K. Yeah. So this is K to pi. This one. This is D to I forgot which one. D to rho maybe. There's B to K is this other line, and then it switches over to a different B decay. Maybe I should have put the exact decay modes, but it's each time. So each time you have this huge jump, is you go from a different initial meson.
Okay. Yeah. Thanks.
And why these heavier ones are less sensitive in this case is because the standard model decay widths are wider for B meson than kaons. They go mk over mw to the 4th power, and mb over mw to the 4th power. So that I will actually try to explain this better in a second. Anything else before I keep going?
No. Sorry to have interrupted.
That's good. Yeah. Thank you, Jim. Yeah. Oh, so that's where I was. So there's this. It's a bit orthogonal, but I thought it was worth just mentioning is that if you have Majorana neutrinos, there is a possibility of observing the case where you would have meant to do that, where you have B to pi and then mu minus. So you change you change lepton number by 2 units. So the reason why you change it is, if you follow this line, that's the Majorana mass insertion. So you can change lepton number by 2 units on the sterile neutrino line, and then you have 2 W exchanges to couple to the standard model quarks, and you emit 2 leptons of the same charge. So it looks like you start with you start with a lepton number 0 initial state, and you end up with a lepton number 2 final state. So this is not flavor violating, it's lepton number violating, but you can also have easily, because we have mixings of order 1 in the neutrino sector, you could have easily mu minus E minus and mu minus tau minus final states. Right? That's sounds more exotic, but it's not really, because we saw that there are these 2 natural ways of explaining the neutrino masses, and unless you forbid these types of processes, they're there. And I'm sure you will argue, not everything that is not forbidden is allowed. So if you don't explicitly forbid, this will happen. So the question is just at what level, and you should go after it experimentally. All right. So so I spent now a bit more time on these searches for light in physics. So I'll go over this argument in more detail as to why we were seeing these jumps and where this came from. All right. So why is this interesting? So one thing that is kind of surprising in this case is if I look at a model where I have a light state, let's call it X, and I look at the decay where I have K to pi X or mu to EX. So you produce this X on shell. These are really very sensitive probes of UV physics, of high scales, very high scales. It's maybe counterintuitive. So you have something light that comes out of your decay. And I'm saying that this is even more sensitive than if I just look at mu to E conversion, or mu to E gamma. So why is that? All right, so the reason is that there's a parametric gain there, compared to probing new physics through these dimension 6 operators that we talked about a lot. All right, so and the reason has to do with the fact that the standard model decay with themselves come from dimension 6 operators. So you integrate out the W, as I think Javier explained, or maybe somebody else. You will end up with this 1 over MW squared suppressed operators. All right. So the amplitude itself will go as 1 over MW squared. If I look at the decay width for some lepton, well, it goes as amplitude squared, so 1 over the MW to the 4th. And to have the dimensions correct, the units right, then upstairs I'll have M lepton, the initial lepton mass to the 5th. So it goes as M lepton over M to the 4, MW to the 4. So it's highly suppressed, for instance, for muon decays. So that's why the muon lifetime is so much smaller than the tau lifetime. All right, so now let's do the following. So let's say if our new physics now, instead of through this higher dimensional operator, just couples to dimension 4 operators. So an example would be a scalar that mixes with the Higgs. A scalar that mixes with the Higgs, you can write down a renormalizable operator. After electric symmetry breaking, the two mass eigenstates will mix. And let's say that the smaller one has a small linear part that is due to the Higgs. So that's how the couplings to the standard model work. So all the couplings to the standard model are suppressed by this small mixing angle theta. This is a dimensionless quantity. Theta is just an angle. It's going to be small. Let's say 10 to the minus 10. Very small. All right. So now what would be the decay width, the partial decay width? So K to pi phi, let's say, is our light scalar, will be proportional to the amplitude squared. The amplitude itself is proportional to this small number. So it goes as theta squared. All right. And then to have the units right, I just have one power of mk. So it's just 1 power of mk. Now for branching ratio, I need to divide with this very small decay width, which goes as mk to the 5th over mw to the 4th. So this branching ratio has theta squared mw over mk to the 4. So you have really a parametric gain because new physics came from a renormalizable operator, while the standard model came from the dimension 6, from heavy exchange of a heavy W. All right, so that's the gain. All right, so another example would be, let's say, if I have dimension 5 operators. So this we will do in the next few slides. All right, so dimension 5 operators means that there's an operator of new physics that is suppressed by the new physics scale. Let's call it FA. And the same exercise will give me a branching ratio that gives me a branching ratio where I have mw squared over fa mu squared. So you see I have this mu sitting downstairs. So just because the muon lifetime is so long, or the decay width, the total decay width of the muon is very, very small, no? It goes as 1 over mw to the fourth. I have a parametric enhancement to this UV scale. No? Now, if we go even further, and I say that the new physics comes from dimension 6, there is no such enhancement. Both the new physics and the standard model come with this 1 over mw to the 4 or 1 over lambda to the 4th. So there are no factors of mu sitting in the branching ratio from mu to 3e if this is coming from heavy new physics. All right, so you see that if I have light in physics, just from the naive dimensional analysis, we expect to have a sensitivity to much higher scales. All right, okay. Now, so that was the upshot, no? So you look for mu to ex, tau to mu x, where x is unshared, so light state, and you'll end up with a very high, like probe of very high scales. Now, the only wrinkle here is that this state x needs to exist. When you search for mu to e gamma, all the final states exist, no? The electron exists, the photon exists, so you're guaranteed to be measuring something, no? The question is whether or not you have a transition that is due to new physics. In this case, you don't know whether this X exists. So how common are these light states? There's an important result, which is that if you start with a global symmetry and you break it spontaneously, there will be an associated Nambu-Goldstone boson, which is massless if the symmetry was exact. Okay. Now, if the symmetry was not exact, you would still have a light boson, but it will not be massless. It will have some small mass. All right. So often this mass of, now we will call them pseudo Nambu-Goldstone bosons, pseudo because they're not massless, they have a small mass. You can take it as a free parameter, which is proportional to this explicit breaking. Sometimes it's fixed for you from the structure. All right, so a celebrated example where this is fixed is the QCD axiom. So I'll say a few words about the QCD axiom, and I think we'll take a break short in maybe 5 minutes or so. All right, so what is this QCD axiom? So it solves the following problem, that in the standard model Lagrangian, if we write down all the terms that are allowed by the Lorentz and gate symmetries, there's one which appears to have a very small coupling. So the one that is you can write down, but seems not to be present at any significant level, is this GG tilde piece. So you can write alpha s over a pi just as a normalization, and then you have G mu nu. G tilde means that you contract with the Levi-Civita tensor, and then to contract all the indices. So that's the way it's written here. Now, the theta itself is not really the physically observable quantity. It's the theta plus the phase that sits in the Yukawa matrices. All right, so that once you do the URS counting and all these redefinitions, and you're very careful about what happens to this GG tilde piece in the effective action, you will see that theta itself is not observable. It's the theta bar, a cousin of theta. It's CP violating. So CP violating means that there are probes which are very sensitive to its presence. Most importantly, the neutron dipole moment, which is, you do some QCD hadron matrix elements, and you'll find that there's, this is 10 to the minus 16 e centimeters times theta bar. You look at the experimental bound, and you translate into the value of bound on theta bar, which is exquisite, no? So this theta bar, which you would think naively it's some order 1 coupling, is 10 to the minus 10. So why is that? No? That's the strong CP problem. Why is theta bar so small? Right? No? So unlike the CKM CPV violating phase, theta bar is extremely small. Why? All right. So the axiom solves this problem by saying that there is a global symmetry that got broken. There's a remnant Goldstone boson. Let's call it theta bar of X. And it has to have couplings which are of the form theta bar GG tilde. Now this theta bar is a dynamical field, and the potential of this the minimum of the effective potential is when theta bar is 0. So that's crucial. Now there's no other CP violating source. This is the only one, and the effective potential will be driven to 0. So no CP violation. All right. So global symmetry. There are many choices. This global symmetry is broken, but such that you have this coupling. And then dynamically, this drives the theta bar, the effective theta bar term to 0, right? So in order for this to work, you need to have this light particle, the axion. So from low energy perspective, now you can just start writing a different terms in the Lagrangian. Since this is a Goldstone boson, it means that there is a hidden shift symmetry, namely the mass term is forbidden, but also all the terms that are not anomalous, so that's the anomalous terms, will come as derivatives. So the first term is just d mu a. So all the couplings of this light guy are dimension 5. So this is the anomaly piece, coupling to GG tilde, another anomalous piece, coupling to FF tilde, and couplings to standard model fermions with some, I just parameterize this with some couplings that can be either diagonal or off diagonal. So the GG tilde piece is the one that will generate the mass term for the axion. So just the fact that this thing will couple to you close the loop with the gluons, it's non-perturbative, you will generate the mass term for A that is down by 1 over FA because you couple to feebly to the QCD, and it's a number, no? It's a number that is fixed by QCD. So in this case, you see the QCD axion. If you fix the scale at which things are happening, this heavy scale FA, the axion decay constant, also called, then it's just a number fixed by QCD dynamics. And it's a very small mass. So the 10 to the 12 GeV is because we will be sensitive to this case with experiments. Another very important realization is that the axion is also a viable cold dark matter candidate, because when the universe cools, there would be coherent oscillations of this axion field, and it will act like a cold dark matter if you're in this regime. So roughly where this mass sits. So roughly the scales that we're counting. All right, so I think it's a good time to take a 5-minute break. And then what we'll do next is we'll look at the, we'll assume that these Flavour violating couplings are present, and we'll try to see if you can probe interesting parameter space that could probe the QCD axiom. Are there any questions before we?
Well, actually, you have an hour break today. Guy,
1 hour. Guy, I forgot. Yeah. Okay.
Guy is giving his last lecture in between.
Okay.
So you have a
bit good. Okay.
That doesn't cause you a problem, I hope. You can
no,
have
okay. Yeah, it's a pleasant surprise.
Okay.
I didn't realize.
No, sorry. I tried to minimize back-to-back lectures if possible. But
good. Yeah. Thank you. All right.
So, but if anyone has an immediate question, if not, we And we continue in an hour. Okay.
I have a small question regarding this gauged U1 Frogut-Nielsen model.
Mhm.
So, hello.
Yes, we can hear
Yeah,
you.
yeah. So, since I mean, you do the charge assignment in such a way that the lighter generation masses arises at the higher order. Are these model typically anomaly free, or you have to do something?
Yeah, that's like it's you enable. No? So this what I told you right now. So the way I explain this, this would be anomalous charge assignments. Yes, so charge the left-handed and the right-handed. So the chiral fields you charge under the U1, and you have phi over lambda. Now there's a I don't know, let's say an incredible really, like I thought this was incredible, no? Is that instead of doing this, you have a different charge assignments where all the vector-like fields are charged, but these guys are not, okay?
Mm-hmm.
So these guys are not, and you forbid the Yukawa by other means from the standard model. Then, well, okay, I should say differently. So there is some structure that you need to put in, which is if you have a supersymmetry, this will be done for you. So only holomorphic pieces in the potential should be allowed. Then you still have the same hierarchy, but this lambda, or instead of phi over lambda, you have lambda over phi. Okay. And it's anomaly free. That's the miracle, no? So you change. So the field content is the same. The charge assignment are different, and you have to have this supersymmetric version where you have certain terms are forbidden. So you only have holomorphic ones. Then it's anomaly free, and that's this inverted Frogut-Nielsen. I didn't go into it. But
okay.
I mean, there's an easy way to understand this, is that you can, sorry, I'm maybe taking guys' time. An easy way of to understand it is that if you, instead of postulating the vector-like Fermi masses, you just assume that these are coming from waves of two guys. One is phi, and the other, let's call it phi f. And it's the ratio between the two that determines in which of the two models you sit. Okay.
Okay. Okay.
You see that it works either way. Yeah.
Thanks.
So these are the last two slides that we went over at the end of third lecture. So we're looking at this solution to the strong CP problem. It says that it's asking a question: why is the theta parameter in the Lagrangian so small, smaller than 10 to the minus 10? And the proposed solution was that there is a number-Goldstone boson that is coupling to GG tilde that drives this theta term to 0. And there are two important predictions. One is that the mass is fixed as soon as the scale of that governs the strength of couplings, Fa, the axion decay constant, is determined. And once this mass is in the right range, you will have also the cold dark matter candidate that can explain the radical abundance of dark matter. All right, so now to a model for axion that has Flavour structure. So the couplings to the fermions were in principle anything you want if you are starting from bottom up. Usually these are taken to be Flavour diagonal, but it doesn't have to be. For instance, this model of flavor, the U1 Froggatt-Nielsen that I introduced, if the U1 Froggatt-Nielsen is global, instead of gauge, it's a global symmetry, then there will be an associated Nambu-Boson model. So there was this series of couplings to the vector-like fermions. The standard model fermions are charged. The U1 Froggatt-Nielsen is anomalous under QCD. The interesting thing is that it comes purely from the fact that the standard model fermions are charged, so that fixes quite stringently this coupling to the Dighe tilde, the one that we want. And the hierarchy came from this series of phi over lambda insertions, so integrating out the vector-like fermions. Now, so where is the QCD axion? The QCD axion is the phase of this Flavon field. So the Flavon field contains a wave. There's the radial mode that will be heavy, but the phase, so the A over F, this guy here, that's the QCD axion. But now it sits in a field that couples differently to different generations. And the reason why it couples differently to different generations is such that it solves the standard model Flavor puzzle. The solution to the flavor puzzle are intimately tied. And you see that this can be quite generic. So it doesn't have to be tied to, let's see. Okay. It doesn't have to be tied to this one Froggatt-Nielsen model. So all we need for this axial mechanism is that there's a global symmetry. It's called the Peche Queen after the inventors of the mechanism that is spontaneously broken. The Goldstone boson is the axion. And this global symmetry needs to be anomalous under QCD. So if this global symmetry is part of the flavor symmetry, you will end up with flavor violating couplings. All right. So in the examples that they will show, we will identify it with the Froggatt-Nielsen E1. All right. So this oxyflavon has both the diagonal and the off-diagonal couplings. The flavor violating couplings to fermions then give us a new handle. All these diagonal couplings are the couplings that are generically used for the axion searches, while the flavor of diagonal ones are present when this global Peche Queen symmetry is part of the flavor group. In this particular model, the strength of the coupling of axion to fermions, let's say the quarks, is just a geometric mean of the masses of standard model fermions divided by this heavy scale, so the UV scale, the axion decay constant. So this FA, you can think of it as the wave of the Flavon field. All right, so numerically, we can convert this to a mass of the axion. Instead of FA, 1 over FA, I can just use the mass of the axion. And then let's put this mass of the axion at the micro electron volt, where this is a dark matter candidate. And you see that this is very suppressed, now 10 to the 12 GeV times the square root of the masses. All right, so can the flavor violate the flavor decays probe anything interesting? So that's what's shown here. So what's plotted is the sort of the usual axion plane, which is the coupling to photons versus the mass of the axion. These grayed out region are the traditional searches that use the photon coupling of the axion. The yellow region is a region for sort of the typical scan over the Flavor diagonal axion model. They have these acronyms after the names of people that first wrote them down. And then the two blue lines, the vertical lines, are the bounds from k plus to pi plus a. So this is the bound from the odd bound. So that's not actually the newest one. Is from 2016. There's an NA60 bound, which is better, but what's more interesting is that the future in NA62, which is this dashed line, has nothing to do with coupling to the photons. No? So it only has to do with the 1 over f. No? So that's why it doesn't matter what the coupling to the photon is. And the experiment is k to pi a. A is so light that it doesn't decay in the detector and it escapes. So you just see a 2-watt decay where you're able to measure the pion, but you don't see the invisible axion. Right? And you can push this on the log scale, you can push this down well into the region where this is a dark matter candidate. All right. Okay. So this is kaons. Where are the muons or the leptons? All right. So in this minimal model, the k to pi a was the most sensitive, but this is not true in general. So we'll ramp up to the case where we'll see a model where this is not true. So right now, let's just focus on the examples where we'll first do a bottom-up approach. So it's just switching on the couplings in this effective Lagrangian will allow for any mass. So not just the QCD axion, but we'll vary the mass. So that will be called what's called an axion-like particle or an ALP. And we will restrict to the case where we couple only to leptons. So just to see the lay of the land, what are the constraints? And then I'll come back to a concrete model to see whether this makes any sense or not. All right, so bottom up, we just switch on couplings to leptons, and let's see what happens. So that's the current bounds on the on such a leptophilic axion-like particle scenario. That's the mass of the ARP, and it's plotted from 100 electron volts to GeV, which is down here. And then the scale, so this decay constant, the axion decay constant, is large now. So that's the excluded regions in gray are from the astrophysics constraints. And they are, for instance, from white dwarf cooling, so you should not change the behavior of white dwarf too much. The red giants cooling, so you should not cool red giants too quickly because we see them. Then there's the bound from supernova. If you assume that you couple to electrons or if you couple to muons, these are these great regions, grayed out regions. The present bounds are from the lab experiments that use lepton flavor violating transitions, are the old one from Argus for tau couplings, the projected Belle II, so again, huge jump in sensitivity. Then there are the present bounds from the Yodidio et al. Experiment measurement, and from Twist in Canada. There are several different exclusions. So this is this green, and it's dashed, solid, and the longer dashed. It gives us the different assumption about the left-handed versus right-handed couplings, and I will go over this in the next few slides. For Twist, this spread is smaller, and the orange and red lines are the projected future sensitivities of two experiments, and I will go over this in the next slides. All right, so the important thing to see here is that the experiments are probing unexcluded parameters, so it's not excluded by astrophysics, and we'll touch base with whether or not this can be a dark matter in just a bit later. All right, so So how do these searches work? So let's look at the mu plus, E plus, ALP decay. So the ALP is not long, so it's long-lived, so it doesn't decay inside the detector. So all you see is you measure the single positron, and you're searching for a positron line. So there are two types of searches, depending on whether or not you have a polarized muon. So if you take care and keep the polarization of the muon close to 1 or -1, so it's opposite to the direction of flight, then the standard model, mu to E nu bar, which has left-handed structure, if you look in the forward direction, so E plus opposite to the polarization of the muon, will have this shape. So the solid line is completely forward. Theta E is this angle away from the forward direction, so opposite to the spin of the muon. XE is just the fraction of positron energy compared to the maximal one, which is basically mu over half, so half of the muon mass. So that's the, if you have a massless QCD axion, or effectively massless, so very small mass, your signal will be a line that sits at the end of this spectrum. And the standard model contribution for left-handed, because of the left-handed structure of the standard model couplings, it dies off in the forward region. Now, it can't be completely just forward. There has to be some opening angle. So let's say if you have a cosine theta of 0.8, all right, that's the standard model background. So the search is finding a line on top of this falling background, but the standard model background is suppressed. Now, if your ARP has left-handed couplings, it will also have a suppressed rate here. If it has, if it has left-handed coupling, the same as in the standard, it will have a suppressed rate. If it has right-handed couplings, it's not suppressed. So you are mostly sensitive to the right-handed couplings, and that's why in the Dighe et al., these lines were spread depending on whether you see the right-handed or left-handed couplings. All right. Now, the other option is that you don't have a polarized muon beam. You can have much more statistics in this case, and you're sensitive to both left-handed and right-handed couplings. The search is the same. Now you're searching for a line in the spectrum depending on the mass. And at the end here, you always have a standard model background. All right, so that was the twist search from 2015. So what were these two proposed searches? So one is what we call MEC2 forward, where you could repurpose the MEC2 detector. So the MEC2 experiment, at the end of the run, of their physics run, they already have polarized muons. So you could repeat the similar search that the Dighe et al. Did in '88. So you could use this polarized muon, stop polarized muons, and just put a colorimeter downstream. There were two lines there. Depending on what you assume for the magnetic field, you either just switch it off, or you can have a big gain of 100 times from focused incorrectly, which is what was done in the Dighe et al. And the lines were for 2 weeks of running. And there are other improvements you could do. Again, a lot of factors. All right, so that were these two lines here. The orange line assumed there is focusing. If you do not focus with 2 weeks running, you basically repeat the Dighe et al. Experiment. Right? Then there's this red line here. That's also the rich mu3e online. So that's a simplified search that mu23e is planning to do. And they what they do is they search on the Michel spectrum. So that's the momentum of the outgoing electron. And you do a bump search, so bump hunt. So that would be the standard model Michel spectrum. You do a bump hunt on top of this spectrum, where you do an online event reconstruction. So you take all the data that are coming out, but you use just something what's called a short track, so less information, only you write down some momentum, and that's it. Also smaller files. And it will be sensitive to both left-handed and right-handed apps. And because of huge statistics in mu-3e, so then there was also the tau decay that I added out. So the challenge here is that you have a tau goes to a muon plus a missing energy, right? So the process is from the standard model decays. So you can never completely reconstruct the tau rest frames where you could search for a peak. It's always smeared. So you can only do some approximate reconstructions, and you boost what's called pseudo rest frame of the tau. You can just assume your best guess about the rest frame of this tau on the other side. And what's even more surprising is that, these are very old bounds. They're shown from 95. And rescaling to what Belle and Belle II could do, so just analyzing the data at Belle, you already can gain an order of magnitude. And then with Belle II, there's another factor of 5 or so, no? Or 3 in this case. But this is naive rescaling, so it depends exactly what you do. No? In other words, there is a lot of unexplored parameter space, and whether or not the muons or the taus are the best option, again, it depends on the flavor structure. So in both cases, there is a good chance you could find a QCD axion, a real QCD axion from lepton flavor violating decays, which sounds kind of but I'll show you second. All right, so more generally, so can this IISc be a dark matter candidate? Now, first thing that needs to be true is that it has to be stable at the time scales of the universe. So it shouldn't decay before now. We don't see any evidence for decaying dark matter. All right, so let's say that the IISc decays to 2 photons. And as this lifetime is bigger than the lifetime of the universe. This is the h0, the Hubble constant. So in here, I just converted this into a numerical statement. This E effective will be a coupling to photons that is already normalized such that this will be order 1 with all loop factors and everything in a typical model. Mass of IISc, which turns out to be 10 keV if FA is 10 to the 10 GeV, which is what you probe with this lepton flavor violating decays. So in other words, MA needs to be lighter than about 10 keV or so to even make sense. So the IISc needs to be lighter than 10 keV to even have make sense to ask that this is a dark matter candidate. All right, so let's see what the exclusions are. So that's this blue region here, just saying that it has to be long-lived enough. You can do better by asking that there's whether there's some extra galactic light coming at us from the decays of the IISc. That's this exclusion. We don't see a line in the extragalactic light. So really, you need to be lighter than, I don't know, 100 electron volts or so. These colored lines are the reach and the exclusion from Dighe et al. So present exclusion is the green one. The two projections from back to forward and the mu to 3e. And then there are all these other searches that some of them really rely on this dark matter to be dark matter to be present in the universe. So it would come to the detector and and give a response. So to say this in a different way, you can discover an ALP that is a dark matter candidate from, let's say, muon decay, mu to e dark matter, but you would not know that it's a dark matter. You need another experiment that then probes the right parameter space that tells you that there's a dark matter particle coming in and gives the detector response. Okay, so what is this? There are more in the backup slides, so I just flash one model for lepton flavor violating oxyflavon. So that's a QCD axion, but which for which the mu to e a is the most sensitive probe. So the reason why this is the case, now that you don't have k to pi a, but mu to ea, is that the Peche-Quinn symmetry is a different global symmetry. So it's part of this flavor, the SU2 cross U1 flavor structure. So SU2 flavor structure is encoding that the first two generations are light. So they're approximately, there's an approximate symmetry there. If you set the masses of the first two generations to be exactly zero, there's an SU2 flavor symmetry there. And this is broken by less than the Yukawas of the third generation. So that's why this structure SU2F cross U1. Now, the fact that you have an SU2 flavor group instead of a U1 Froggatt-Nielsen has the following consequence, is that all these flavor violating couplings now needs to go through the third generation. Right? So you always need to go through the third generation in order to get the flavor changing transition, flavor changing neutral current. For quarks, that's a big price to pay because the CKM elements are small. While for leptons, it's not a big price to pay because the mixing angles are big. So this PMNS matrix has big mixing angles between first and third, or second and third, especially second to third mixing angle, right? So the end result of all this is that the K to pi A is suppressed by these extra CKM mixing angles, but not for the leptons. In the leptons, you have big mixings. So mu to EA is the most stringent constraint. So if we are now for this SU2 oxyflavon, so QCD axion that is part of this non-abelian global symmetry. If we plot the constraints, so the grade 1 are searches that use the photon couplings. These dashed lines are future projections. The blue lines here are these two exemplary models that are not the oxyflavon. So you have only the flavor diagonal couplings. And then this dashed line, sorry, this red line is the prediction for the mass in this particular lepton flavor violating oxyflavon model. There, and then these vertical lines are the different bounds on the lepton couplings. So this is the present bound from the Whiteworth cooling. The mu to EA present constraint is here, and with the mu to 3e feature, which you would push beyond the astrophysics constraint, and you would start to probe this this region that is not explored yet. All right, so again, you know, it's a kind of surprising, no? So this is a QCD axion that just discovered from the leptophilic couplings. If it lives, you know, somewhere here, no? So if it lives on this line, right? So you would not see it through the photon couplings, through the couplings to gluons, but through a leptophilic interaction, no? Which is maybe a bit surprising. The reason why is that this lepton flavor violating experiments are very, I mean, these are very stringent constraints. They probe really very small branching ratios. All right. So now I'll switch gears completely, and I'll talk about a different probe, again focusing on lepton flavor, which is Higgs. No? The Higgs is the origin of flavor in the standard model, but we can also use it as the initial state that decays, and then from its decay products, we can deduce whether or not this standard model picture about the generation of fermion masses is correct or not. All right, so let me say a few words about that. All right, so the standard model Higgs plays two. So the first one is it breaks the electroweak symmetry. So it gives masses to the W and the Z boson. And then a completely different role is due to the Yukawa couplings to fermions. So it also gives the masses to the standard model fermions. So how well have we tested this? So the fact that the electroweak symmetry breaking is due to the standard model Higgs, no, is quite well tested. We'll focus mostly on whether the fermion masses, you know, these red balls and the blue balls, are coming from the Higgs. All right, so that's the particle mass versus the coupling to the Higgs in some units. No? So it's all normalized to the wave of the Higgs, and then the mass of the Higgs. And depending on what exactly the expression is for the standard model value, no? There's either a square root sitting there in front of this kappa or not. The prediction, all these are predicted to lie on a line. No? So in the standard model, they should lie on this line. So the coupling to the Higgs should be directly proportional to the mass of the particle, and there are particles of different varieties. So that's the top quarks or fermion, and then the gauge bosons W and Z, and then the bottom quark tau lepton and the muon, and they're also color coded. So the red ones are third generation fermions. The black one, you probe electroweak symmetry breaking. So the fact that this lies on this line tells me that electroweak symmetry breaking is coming from the standard model Higgs predominantly. And there's one single guy here, the muon, which is not the third generation fermion. Right? So all the fermionic coupling are probing whether or not the flavor structure is really due to the simple coupling to a single Higgs. All right. So no sign of new physics at LHC. So I'll talk about this Higgs coupling in terms of the effective field theory. So either there are two options here. So either you assume that the Higgs itself is a doublet, and then you integrate out the new physics and you write down a standard model, what's called the standard model EFT, where this would be a standard model Yukawa with a Higgs doublet, and then corrections. This is the dimension 6 operator. So 2 fermions give me dimension 3, and then 3 Higgs fields gives me another dimension 3. So that therefore it's suppressed by 1 over lambda squared. Now there's a version of this effective field theory where you don't assume how the standard model electroweak symmetry, how the electroweak symmetry is broken, and already just write an electroweak in an electroweak broken phase. So that's called the Higgs effective theory. So Heft. And there's something called the kappa framework, which is nothing more than you only look at dimension 4 couplings in Heft, and you go in a particular gauge, the unitary gauge. All right. So that's the one that we will use mostly. So in this Heft Lagrangian, so I have a mass of the fermion, and then there are couplings to the Higgs. So you see both of them are dimension 4, no? So mass is GeV, and then 3 powers of GeV for the fermion current, scalar current, and the same thing here. Now Higgs is a scalar, so dimension 1, and then dimension 3 for the couplings. And there's nothing, there's no, just in this Heft, there's in principle no relation between M and Y. All right, so this is written in a slightly different way. So that's why the kappa framework jargon is, so let's assume that this, this Yij are something close to what the standard model would predict. So let's normalize them to the standard model value, which would be MQ over V, so the VEV, and times the fudge factor, the parameter. So kappa Q will be 1 in the standard model. There's the CP odd version where I have a gamma 5 sitting here, I gamma 5. Let's call this kappa tilde. So kappa tilde is 0 in the standard model. And then you can also have flavor of diagonal. So let's just put 2 labels there. So QQ prime and kappa tilde QQ prime. So I wrote this for the quarks. It's the same for the leptons. So exactly the same notation. All right. So now I have the notation. So let's look at what are we really testing with the Higgs. So we're testing this prediction, that the Yukawa coupling of the standard model is directly proportional to the mass over the VEV, mass of the fermions. So this implies very hierarchical couplings. So top couples most strongly, and then successively couple less and less to the Higgs. Electron as the super suppressed 10 to the -6 coupling. So that's a clear experimental prediction that you can test. All right. So there are really several questions that you can ask. So the first one is, are these couplings proportional to the masses? Is this factor the right one, the square root of 2 over V? So that's the first is, do this fermion lie on a line? Is this line, does this line have the right slope? This MF over V in the kappa notation. Now, what's not plotted here is whether there are any non-diagonal couplings. So whether there's any Flavour violation. Are there any Yukawa couplings that are you will have CP violation. In other words, in standard model, these Yukawa couplings need to be real. Imaginary parts are 0. Are there any imaginary parts? All right. So how is this proportionality factor tested?
So
yes.
Yeah, sorry, I have a question again. So for these off diagonal elements, Does it maintain the same sort of? Does it have to have the same sort of hierarchy whereby it's going to more likely to couple to the third generation or the heavier ones, or can
that's
you
a good question.
end up with a large off-diagonal element that couples to a first generation or a second generation?
Yeah, so there's okay, you can make a model where the off-diagonals will be bigger than you would naively expect. But a rule of thumb is, so unless you are very careful, a rule of thumb is that you will end up with off-diagonal elements that will be very big, and then you will need to explain why one of the eigenvalues is very small. No? So let's say you have large entries, and magically there will be one of the eigenvalues will be very small. You can do this with a symmetry, no? But generically, you would just say, okay, there's an interesting part of the parameter space where the off-diagonal elements don't introduce any fine-tuning when you diagonalize. How big is this? Well, if they are the geometric mean of the diagonal masses, then when you diagonalize, you don't have any large constellations. And that's kind of a rule of thumb, a good target experimentally, because then you really start to probe many models, no? And there will be a line on the exclusions where this will be denoted, no? So you will see where this line lies, and different final states we're at different stages, no? And I'll also comment on this, but it's a very good point. Yeah, you can in principle write models where you would have enhanced flavor violation, but usually you need to be below this naturalness.
Okay, yeah, so you'd have to fine tune, which is obviously you'd like to avoid, but
right, with a symmetry you can do it. No, I mean you can just assign flavor charges such that you will forbid diagonal coupling. No? You can do it, but it's I mean far from generic. No, you need to work quite hard to make it viable if you want to do that, because there are other constraints.
Okay, thank you.
Yeah, good. Okay, yeah. So I'll walk you through these different tests. So the first one is the factor of proportionality. So what goes in is you measure the production rate and the branching ratio of the Higgs to diagonal final state. No? So for instance, you will have a Higgs that decays to a B, tau, and a muon. So that's just from the coupling tree level. No? So it's just you cover coupling. If you want to measure the top coupling, however, Higgs is not heavy enough. So it's lighter than the TT bar mass. Production of TT bar. And then there are also sensitivity from the decay, for instance, Higgs to photons goes through this loop. So there's sensitivity to top and B quark couplings, as well as the couplings to the W. Right? So by measuring all these modes, you end up with these measurements here. No? So you need to disentangle contributions to the production and the decay, and then you translate this into the measurements that are plotted here. Okay, so so we really want to sort of test the flavor of the Higgs. No? So what is this? The fact that the muon is much lighter, telling us about the Higgs, is this was, I would say, a very interesting question, and was whether Higgs only couples to the third generation or also the first two generations. And to answer this is a very tough question. No? Apart from the muon, we have almost no handle. There's a less a strong statement that you can make. We can ask whether the couplings, if they exist, are hierarchical. No? For all the other guys except for the muon, we can show this. Only this, no? So not the existence, but that there is an upper bound which is smaller than 1. So if I ask whether the coupling to the electron or the muon upper bound, all right? For the muon, there's also a measurement which is qualitatively different. For the up and the charm, similarly, no, it is much smaller than the top, and for D and S, you don't know that it's smaller than the bottom. All right, so it's a pretty weak bound. All right, so you see that this point that there's a measurement of the muon Yukawa is really, I would say, a qualitatively new feature, very different, no? Because that's the first. So this is from 2 years ago. No, was the first real evidence that the Higgs couples to the second generation fermions, and it's probably the only probe that we'll ever have. No, all the others are too tough. You can't measure the couplings to electrons and the strange and the C. Maybe the charm, if we get lucky with high Lumi LHC. There's some chance there. But muon, it's basically the only probe we have, and it's already pretty well measured. No? So this normalized coupling, it's basically one within 20%. Now, before this measurement, what could happen? You could have a 2 Higgs double model where the Higgs that we see couples to the third generation, and the other Higgs couples to the first 2 generations. And you see, I mean, to make up a muon mass, you only need a very small vacuum expectation value. Now, a VEV that gives you a muon mass of 100 MeV, it's a very small VEV that you need from some other source. You'll never see this from measuring the electric symmetry breaking sector. So couplings to Z and the W. So, you know, the fact that, so the muon mass breaks the electric symmetry, you know, where does this breaking come from? It comes from the standard model Higgs. That is incredible. It's incredible because it tells you that it comes not from some small VEV that has nothing to do with the standard model Higgs. It comes from a small coupling, so dimensionless coupling that sits in front of the Higgs. So that's really, it's really a qualitatively very, very new thing. It came from, I'm showing a little bit more of the details. So this is a combination of measurements in different production channels. So, and in all of them, you see which is, say, 3 sigma-ish evidence. All right. So that was for the proportionality, so the diagonal couplings. So I'll say a few words about the Flavour violating Higgs couplings and then the CP violating, and then I think I will stop. I will skip the G-2 with the muon. All right, so Flavour violating Higgs coupling. So if you see them, that's new physics. So in the standard model, it's diagonal. And for Higgs to tau mu and Higgs to tau e, you can see this at the LHC, so directly looking at this final state. There are also indirect bounds from our beloved charged lepton Flavour violating mode. So tau to mu gamma, tau to 3 mu would also, they also constrained these couplings. For instance, you can have a loop like this where you have tau spits over Higgs virtual, and then you have a tau mu coupling. You close the loop, you emit a mu, a photon, and you have tau to mu gamma. There's a 2-loop contribution to it that you need to take into account. And then there's tau to 3 mu also. Now you can have a 3-level Higgs exchange where you have a tau mu Flavour violating coupling and Higgs couples to muons on this side. All right. So how how do they compare with these direct measurements where you produce a Higgs and this decays? So that's what's shown here. So this is the two chiralities, so either left-handed muon or a right-handed muon. You don't distinguish between them in the Higgs decay, so that's why these are completely symmetric. The tau to 3 muon is excluded up to this level. Tau to mu gamma excludes the coupling at the 10 to the minus 2 level. And then what is observed, is this black line. And it sits right on top of the expected band. So the green and the yellow are the so-called Baselian plots. So the green is the 1 sigma expectation as to where you expected this bound to be. So Higgs to mu tau from CMS, it's right on top of the expectation. And this line here, the blue line, is a line where if you push the bounds below it, the product of off diagonals becomes smaller than the product of the diagonal standard model coupling. So now, once you're below this line, you are in a regime where having off diagonal Higgs couplings no longer requires some cancellations when you diagonalize the mass matrix, right? So this is the natural region. If we look at the Higgs to E tau, so tau to 3e, tau to E gamma, are the indirect bounds. The observed Higgs to E tau is the black line, right? Space is still within the expected range, but in this case, the bound is not so stringent. No, you see it in most of the parameter space, you sit above this naturalness expectation. Also, if you are, let's say here, you see these two off diagonal couplings. If you had the signal, it would require some cancellation when you diagonalize the mass matrix. All right, so now let's turn this into a question about which scale you are probing. So these Yukawa couplings in SMEFT have an expansion which starts with a standard model. And then we have this dimension 6 contribution. So it goes as v squared over lambda squared. If we take this lambda, the coefficients to be order 1, so 1, you're probing 5, 4 TeV mass scales, no? So it's sort of electroweak with big dimension 6 couplings, so no flavor structure there. All right, the Higgs to E mu is quite different in the sense that these indirect bounds are very stringent. So mu to 3e, mu to E conversion, and mu to E gamma are these exclusions here. No? So all of this is excluded from indirect constraints. And the experimental reach is roughly here. So in terms of this naturalness, where you would want to be, below this line, it's not so bad. However, you already have better probes, no? So unless you have some huge cancellations in these indirect searches, you need to have a sensitivity to branching ratio of Higgs to E mu, which is at the 10 to the minus 8 level. So that's these numbers that are shown here. So you need a Higgs factory plus. No? So just Higgs factory is actually not good enough. All right. So I said the last topic will be quite short. Is I'll say a few words about the CP violating couplings. Because that was the final test, is that you don't just have the CP conserving, but you could in principle have a CP violating piece. In standard model, this kappa tilde is 0. It can arise from dimension 6 operators if they have complex coefficients in front. Now, in here, there are very strict are available from LHC B. We're halfway there. The amazing thing is that if you improve a bound on the electric EDM, the scaling will be linear. No? So this is, you're really measuring the matrix element. So a 10 times improvement in the bound on the EDM means a 10 times improvement on this kappa tilde. There is a connection with baryogenesis, but I will not really touch to this. All right, so I'll give you just two examples. There are many more. So all of these are constrained indirectly from the contributions to electric dipole moment. But let's look just at the coupling to the electron. So here you need to assume that the Higgs couples to the top with the standard model coupling. And then you have this two-loop contribution where this box thing, if it's CP violating, it would induce an electric dipole moment for the electron. So under this assumption of standard model Higgs to top coupling that you can test, you get a pretty severe bound on the kappa E tilde. No? So remember, so this is already normalized to the electron mass, and this is much better than the already very small electron you cover. So this really drives home, I think, how sensitive these electron EDMs are. Right? So, okay, it's a bound, not a signal, but you could in principle see a signal. The other thing is one of the two, so Higgs to top, you have the same sensitivity. In Higgs to tau, you can directly measure CP violating couplings from the Higgs decays. And the reason why you can do it is the tau, when it decays hadronically, these decays carry information about the polarization of the tau. If you compare the two decays, the tau plus and tau minus, you construct the angles from either two-body decays to a pion or the three-body decays, so all these decay modes. So two-body, three-body, or single pi plus neutrino. You can construct different planes. They all have to do with pion, where the pion is, the charged pion. You will be sensitive to, so this phi CP, which is the angle, okay, some more complicated geometric construction, we could go over this. But the important thing is that you're able to, with how the charged pions are distributed in the phase space, you are able to track the spin of the decaying tau. And this angular correlation will be different whether or not you have CP violation in them. So this phi CP will be, for instance, you don't have coupling that is CP conserving for the tau, but you have completely just the CP violating one. That's the green line. Is very different than for the CP conserving case. No? So this phi CP, phi tau tau, is the angle between these different planes that you constructed for the tau decays. And this was done, and that's the resulting constraint. No? So this is kappa T tilde versus kappa, so kappa tau tilde versus kappa tau. Yeah, I'm tethering through the phone now, so that seems to work. Yeah, so I just said, no, it's very high, we have sensitivity to high scales. They're both light and new physics, light and heavy new physics is being probed. And I didn't cover, but there's these experimental anomalies involving muons. I think this makes it even more interesting to go after lepton flavor violating the case.
Okay. Thank you, Jure. I think we may have lost you. I don't know if we lost you on the slide before this, actually.
Oh, already. I see. Okay.
We may have lost something.
So I skipped.
Okay.
All this.
Okay.
So I skipped the flavor. The flavor diagonal probes were there just because maybe if I had enough time, but since I was not charged with this, I don't have to cover it.
Yeah,
But
I think
yeah.
there'll be some discussion of this on Friday.
Well, okay, good.
Andreas Krivelin and Chris Polly and people will speak about this. Okay.
So
okay.
the last thing I wanted to show
Yeah,
really
yeah.
is this. Yeah. And then I just skipped over this. People can ask me questions if they want to, but
So for these flavor violating Higgs decays, I know it's very difficult to do, say, like Higgs to CC bar or something, but are there people looking at like Higgs to I guess what would be BS, right, or something, where you'd have strangeness tag jet and no B tag or an anti B tag or something on the jet. I guess this might be interesting, right, with these models.
Yeah, well, it's very interesting in principle, but in practice, it turns out that you need big statistics. I mean, huge statistics.
Yeah.
So what has been? I mean, there's maybe something that has been missed, but who knows now? So, so Higgs to CC bar, you do charm tagging, and since LHC B is pretty good at it, no? They have a shot at measuring slight increasements. So, like if it's a factor of 2 above the standard model, they might be already sensitive at the end of high Lumi, at the end of high Lumi LHC. You know, I mean, maybe there's some improvements there. I don't know. Like, who knows? No, people are creative. And as we heard, now that's the future of flavor is LHCb, so maybe.
No, guys, we shouldn't believe everything he says. Okay, so
no, but I think that it's actually. I mean, it's really. It's probably worth investing some effort. Now people can have creative ideas there. So there's a shot there. If you want to do anything else, it's pretty tough, no? Because so direct Higgs to strangeness, that's a tall order, no? I mean, in a hadronic environment, that's really, really tough. So what was done is you could try to do this at, you know, FCCEE. And even there, it's not easy because you don't have enough Higgses. You could do an exclusive version, which is Higgs to phi gamma, where you have phi inside the SS bar. At the 100 TV, you still don't have enough statistics. No? I mean, it's amazing. No? It's really huge samples that you need. So that's why this Higgs to, and then Higgs to E plus E minus, you could do if you sit on the resonance for a year. So you sit on the Higgs resonance, let's say you have a muon, like, okay. You have an E plus E minus collider, you sit on the resonance, you will start producing it in a year. With a very good beam control, extreme beam control. So that's why, you know, stressing this that was measured. That's you know, the one probe we have, and seeing some deviations there is easy to imagine because there's such a small thing that you need to do. No, you have it's 100 MeV, so you just put in a little bit of extra electric symmetry breaking in there. It can drive it away. No? That's I mean, it's amazing. No, this is 100 MeV. No, it's a very small coupling. That's why measuring this is very important. I think, as precisely as possible.
Okay. So, any other questions for Jure? I know this has got.
I have one small questions regarding this LHC flavon. So if the axion has mass, let's say less than 10 to the power minus 3 eV, there can be also LFV decays of heavy neutrinos to light neutrinos, no? Maybe tau neutrinos to mu neutrinos emitting axion. Are there constraints from neutrino disappearance events in the oscillations experiments on that?
Yeah, I think I got half of it because there was, okay, sorry, my internet is really, I'm on the phone now. But I understood that, are there any constraints on axions from the neutrino physics? That's what I understood.
Yeah,
Is this
yes.
correct? Yeah,
Yeah.
good, yeah. So in principle, yes. It's tougher than if you have a scalar. So the reason is that this ARP guy, it's has pseudoscalar couplings. So you don't have the coherence. So if you have a scalar exchange, you would modify, for instance, it would have spin-independent couplings. And you would, for instance, have a much bigger response in the coherent scattering, coherent experiment. You don't get it in the oscillations. No, it's not part of the oscillation because you need to go from left to right. It's correlated to sleeping. Then there are constraints from the neutrino self interactions, which come from the CMB. You modify the CMB spectrum. There it doesn't matter so much, no? It's just a light guy, axion or scalar. The important thing is you have a 4 fermion neutrino interaction, and that's a pretty important constraint, no? So that works until if you're in the very low electron volt regime, and it slowly peters out. At some point, the k to pi or k to mu nu, where you meet this guy from the neutrino, takes over. And then again, it doesn't matter whether it's spin or spin, yeah. Or B, no? If you go to heaven, then it's a B that came out. So there are constraints there.
Okay, thanks.
Okay. So I think if there's nothing else, thank you very much, Jure, for these.
Well, thank you, everybody. Yeah.
That's very, very nice.